Hello everybody, it's Mrs. Avon. Today we're going to be leaving the world of planetary motion and we're going to come back to more earthly motions. We are going to do a brief introduction into Chapter 8 during Chapter 9, but it's just going to be a short 1 or 2 day lesson. So here we're starting Chapter 9. In Chapter 9, Section 1, we are going to talk about impulse and momentum. Linear momentum can be simply defined as a mass in motion. It's basically a measure of an object's inertia, and we have talked about inertia in previous chapters. Because we're talking about a physics term, it also has an equation associated with it. Linear momentum is the letter P. So momentum is equal to an object's mass, m, times an object's velocity, v. Therefore, the units for linear momentum are kilogram times a meter per second. Momentum is also a vector, and because the only vector in its equation, mass, is scalar times velocity is vector, since the velocity is the only vector, the momentum follows the direction of velocity. So if I have a rightward moving object, I can calculate its momentum, and I know that it's to the right. If I have a leftward moving object, I can again calculate its momentum, as long as I know its mass and velocity, and its momentum is to the left. We can also calculate the change in momentum of an object. So we use delta P, triangle is delta, which just means the change in momentum. There are 3 different ways to write the same equation. If I write m delta v, that means mass times the change in velocity. Therefore, the change in momentum. I can also take the change in velocity and write it as a parentheses Vf minus Vi. So I have the same equation, just written in a little different terms depending on what variables you have when you're trying to solve a problem. The third version just takes the m and distributes it. We could also write out delta P to be P final minus P initial, depending on what the problem is asking us for. So not only can we calculate an object's momentum, we can also calculate its change in momentum. What happens if the velocity of the object is changing? And what we are going to find is that to create a change in momentum, we have to apply what is called an impulse. An impulse is defined by its equation. It is the force acting over a time interval. So the equation is F delta T. Delta t means the change in time, and typically we just write that as ft. You'll see it on the physics classroom as f times t, because just like in the motion equations, we realize that that t stands for a time interval, the final time minus the initial time. And because a force is measured in newtons, and time is measured in seconds, the units for impulse are newtons times seconds. So we're just taking what we have already learned about force, time, mass, and velocity, and we're applying them to 2 new terms: an impulse, force times time, and momentum, mass times velocity. What we are going to find is that there is a very important relationship between impulse and momentum, and it is called the impulse-momentum theorem. And it says that the impulse is the cause for a change in momentum. So they're numerically equal to each other. So the impulse measured in Newton seconds, a force times time, is equal to the mass of the object times its change in velocity. So we're looking at a cause and effect relationship. If I apply a force to an object for a given amount of time, that object will change its momentum. And although they appear to have different units, if we break down Newton times a second, it becomes a kilogram times a meter per second. So typically we measure impulse in newtons times seconds, and we measure change in momentum, just like we do momentum, in kilograms times a meter per second. Those are in fact identical units. And just like we could with the change in momentum, we can rewrite the impulse-momentum theorem in several different versions depending on what the problem is asking us for. So F delta t equals m delta v. Impulse equals change in momentum. Or I could write it F delta t equals m parentheses Vf minus Vi. That's just breaking down delta V, or the change in velocity, to its final minus initial. And again, I can distribute the m to be mvf, which represents the final momentum of the system, minus mvi, which is the initial momentum of the system. Just like momentum, impulse is also a vector, and it is a vector because of the force. So the impulse is going to follow the direction of the force. So if I have an impulse that's in the same direction as the initial momentum, the object's going to speed up. If I have an impulse that is in the opposite direction or resisting the motion, the object is going to slow down. So I can take these concepts that I've learned in previous chapters and apply them to the impulse momentum theorem. And one of the first things that we're going to look at is just some definitions from the physics classroom. So I just want to remind you for MC2 to be very careful, because there's several different versions of the same problem. This one is asking for the final momentum of this object. Sometimes it will ask for the impulse, sometimes it will ask for the change in momentum. Remember that as long as you have F and T, or m and delta V, you can find the impulse and the change in momentum because they are numerically equal. If, however, it's asking you for the final momentum, you have to rearrange the equation that is at the very bottom of this flip chart and solve it for its final momentum. Remember that a resistive force implies that it's in the opposite direction of motion, so it will subtract, and then that should make that equation very simple for you to use, and those sublevels very easy for you to understand. So I hope this is a nice, quick introduction that will allow you to start applying what we already know to two new concepts: impulse, momentum, and how they are related to each other.